So let's look at the a posteriori error estimate. Okay. All right. Recall that for HFEM we have a algebraic convergence. So again, if we express, if you remember that a priori error estimate was less than or equal to C1 multiplied by H to the power of beta H norm of U, energy norm of U. And this is giving us the algebraic convergence. Well, it turns out that this inequality is actually pretty sharp when your mesh is fine enough. So when we get the so-called terminal convergence, so when asymptotically, this is a very sharp estimate, okay? So we can replace that by an equal sign, okay? Well, if you recall, we can relate the norm of U it was basically the square root of our strain energy. Remember, capital U is reserved for strain energy. And since this is U and not UH, in this equation, U is the exact strain energy. All right. If you remember, the strain energy was also related to the bilinear form, right? So U was equal to 1/2 of my bilinear form applied to U comma U. These are some equations that we wrote in long time ago. Okay? All right. Now I want to look at the norm of U minus UH, and then this is going to be the error squared. Then this is, of course, 1/2 of B of U minus UH comma U minus UH. Again, by just looking at these expressions here, we get that, right? Well, this is actually equal to 1/2 of B U comma U minus 1/2 of B UH comma UH. And there is a theorem in the book that is actually showing this, where you can actually say that this expression here on your right is some sort of error in strain energy, which is basically your U, big U, or uppercase U, minus your UH. That is the approximate value of the strain energy that your finite element solution is going to obtain. And well, given this expression here, right? So if I take this guy squared, and that is equal to this guy, it also has to be equal to what we see here on the right. So this whole expression is going to be equal to C1 squared H to the power of 2 beta H U. Okay? And so we have one expression that says U minus UH is equal to C1 squared H 2 beta H U. All right, if we take a look at this, we have how many unknowns? Huh? 3. What are the unknowns here? Sorry? C1, BH, and U. So how many equations do we need? 3. So we have 3 unknowns. C1, beta H, and U, and so we need 3 equations. All right. So how do we go about defining these 3 equations? What do you think we can do? Well, let's take a look. We know, for instance, that here H is something that we know, right? And with an H, there is going to be an associated UH. So what can we do? Do it multiple times. Exactly. So we take three different types of H. So three different mesh sizes. H0, H1, H2. And then we can get to write this expression three times, right? We have U minus U, H0, C1 squared, H0, 2 beta H, U. U minus U, H1, C1 squared, H1, 2 beta H, U. U minus U, H2, C1 squared, H2, 2 beta H, U. Okay, say this is my equation 1, this is my equation 2, this is my equation 3. Okay, so now I'm going to take the log of 1 divided by 2, right? So I take this guy, I divide it by that guy, and then I take the log of that. U minus U H0, U minus U H1 equal to 2 beta H log of H0 divided by H1. Notice that, of course, when I divide, the C1 square goes away. And when I take the log, I take down the exponent. I can do the same, and I can take the log of 2 divided by 3. So then I get the log of U minus H1 divided by U minus U H2. And then I have the same thing here. Beta H log of H1 divided by H2. So this is going to be my equation 4. This is going to be my equation 5. And now I take 4, I divide it by 5. So then I have the log of U minus UH0 divided by U minus UH1 in the numerator, log of U minus UH1 divided by U minus UH2 in the denominator is equal to the log of H0 divided by H1 in the numerator, log of H1 divided by H2 in the denominator. And I'm going to call this ratio Q, right? And so you could say that the log of U minus UH0 divided by U minus UH1 is equal to Q multiplied by the log of U minus UH1 divided by U minus UH2. And then you see that we get into a nonlinear equation of the form U minus UH0, U minus UH1, right, is equal to U minus UH1 divided by U minus UH2 to the power of Q. And this is a nonlinear equation. So given quantities UH0, UH1, UH2, then Q, which is something that we know because we can compute Q basically by looking at the finite element mesh sizes that we chose, we can compute Q. And so we just have one equation with one unknown, and we can solve for U. And again, U is going to be an approximation of the exact strain energy. So this is what we can use to do convergence analysis when we don't know the exact solution of a problem. Yeah? Okay, well, this is in the case where we are looking at the mesh size, but remember that we also know that the mesh size and the number of degrees of freedom is also related, right? Remember here D was the dimensionality. Okay, well, if H0 divided by H1, then it's basically N1 divided by N0 to the power of 1D, 1 divided by D. And the same thing we can do, for instance, for H1 divided by H2 is equal to N2 divided by N1 to the power of 1 divided by D. So then our factor Q can also be computed as the ratio of things that we know, which is the total number of degrees of freedom. So it's the log N1 divided by N0 divided by log of N2 divided by N1. Okay, and this is perhaps the in my opinion maybe the most important part, the ability that you have right now by simply doing three different finite element analysis on three different meshes, right? And then you can compute an approximation of the exact strain energy. Remember, it's an approximation, but it is still a very, very good approximation. And you will see in the project that it's going to deviate just slightly from the exact strain energy. For the 1D problem, it's very, very, very small, right? And obviously, well, if you want a better approximation, what would you do? Say you are not very happy with your approximation. You take this, you compute this U, but then when you do convergence analysis, the results that you're not getting are not according to theory. So what do you do?
Could you add another equation?
Yeah.
Another mesh?
Exactly, that's what you do. So you go finer, and then you discard the coarser, right? So you always take your three most refined meshes to do this computation, and then you get more and more accurate in the result of the exact strain energy, right? And now you have a way to figure out whether your solution makes sense, right? Because now you can do convergence analysis on problems that do not have an exact solution. Yeah. Okay, so how do we test our formulation? Well, you saw already with Martin on Wednesday, you saw that, well, if you want to check for a quadratic approximation, it makes sense to solve a quadratic problem, right? If you solve for a quadratic problem, your quadratic approximation should give you what error? Zero error. Yeah? You should not get any error from your simulation. Okay, well, let's try to generalize that, right? We're going to move into what is called high order patch tests and construction of manufactured solutions. Okay. So many years ago, there was this scientist Irons, and he devised a so-called patch test. So the patch test, back in the day, when people were trying new types of finite elements, they would create a little test where they would say, well, my element is good enough because if you passed the patch test, that back then meant that your formulation was going to result in convergence. So as you reduce the size of your elements, right, the strain or your stress in your element would remain constant, right, and this would guarantee convergence. So this was the test that was used back in the day. So essentially, actually, if you look at the code that I gave you, there is a patch test there. Have you solved the patch test? It's a two-dimensional problem with quadrangle elements. Yeah? So that is a patch test. It looks more or less like this. All of these are quadrangular elements. Good. And then, well, here we have rollers. Here we have rollers. And well, you would expect that to deform in such a way that if your element formulation is correct, the state of stress for that problem would be constant. So that was the patch test. Well, but we can now generalize this, right? We can say now, let's say I want to test that I have a cubic formulation, right? And I want to come up with a way to test that my cubic formulation makes sense, that it gives me the same thing that you did for the quadratic problem on Wednesday. Then I would like to do the same for a cubic formulation, because now I'm checking my P-FEM implementation for P equals 3. So what do you do? If you want to solve for a cubic problem, what do you do? You assume that you have a cubic approximation, right? You know the cubic approximation, you know the exact solution, and then you calculate. What do I do if I have U? What do I do with U? You put it where? I have my exact solution. I assume it's a cubic. So what do I do with that? I put it where?
On the boundary where stress is applied.
Nope. Yeah.
Do you already have a problem for that exact solution?
You have the exact solution. Of course, you have a problem. You're trying to solve linear elasticity. Okay. So now you assume that you have a cubic polynomial as your exact solution. So what do we do now?
Boundary conditions?
Not yet. Yeah. Obviously, later when you solve the problem, your boundary conditions have to satisfy your exact solution assumption. Let me complete this while you think of it. Ux here is linear. then my stress is constant. Any ideas? Yeah, normally we're given a few things, right? And we don't know U. So we're giving the body force, we're giving, the constitutive law, and then we apply the forces into our problem. We know that the boundary value problem that we are solving, we apply boundary conditions, and we obtain an approximation of U. Okay? Now we are like back engineering. We have the solution. So if we have the solution U, what do we need to get to solve the same boundary value problem?
External conditions, so the body forces.
The body forces. We get the body forces. Right? And then once we get the body force, obviously we solve the problem, and then we're going to get a solution. Okay, so if I'm testing my P3 implementation and I'm solving a cubic problem, right, I should get the cubic polynomial, right?
Yeah.
I assume that I have an exact solution that is cubic. I plug it in my differential equation, I get the body force, and now I solve the problem with my cubic polynomial interpolation. I should get what error? Zero. Zero error. I should get the exact solution. Okay, so this is something called method of manufacture solution. So essentially what you do is you create a problem such that the exact solution U of x belongs to some space that you want, like cubic, quartic, quintic polynomial, right? So essentially now that we have chosen U, then we find the problem that we're going to solve. So what does that mean? Well, we know that elasticity, our equilibrium equation looks something like this, right? So the moment we take and we plug U here, we can basically get what would be our body force. It's negative, of course, right? And then we solve the problem. Keep in mind that now it's UH plus F. That is my body force equal to 0. We solve it. And obviously, we have to account for the right boundary conditions, right? So U is equal to U bar on gamma U. And then T, which is attraction, which is sigma of U dotted with N on gamma T. And that is the way we can try our formulations. And it's very simple. As you saw in the last Wednesday, that is the way we would normally test our quadratic implementation, right? So we take a quadratic function. In this case, it was very simple. It was x multiplied by y minus x, right? So that is a nice parabola. And then we said, well, we're going to solve it with a quadratic interpolation with one element. So very, very simple, because I know that my boundary conditions at the ends of the nodes are 0 and 0. And so essentially, everything boils down to 1 degree of freedom problem for that example. And then you get, wow, I got the exact solution. So now I can have faith. I know that my quadratic implementation is okay, or at least up to that point, because then I need to check all the things, right? Okay, so I say now that my formulation works for one element. So what will you try next? Yeah, that's it. You try for 2 elements. And if you work for 2 elements, it will most likely work for 10 elements. Well, you take it for 10 elements, right? You blindly go for a leap of faith, and then, okay, it works for 10 elements. Wow, cool. Now I have faith that my quadratic implementation is working. And, well, does it work for any Young's modulus? Maybe not. Maybe I want to try that. Next. And then, when you tried all these things, you are confident in that your quadratic implementation is working. That basically means that if you do, or you solve a more challenging problem, and you do your error, your convergence plot, right? The slope that you get should be equal to h, log of h versus log of the error in the energy norm.
Oh,
And
the polynomial order that you chose.
which is
H. No, the 2.
2. So now, not only you have made sure that the problem worked for your manufactured solution, quadratic polynomial, but then you tried on a more hard problem, and you figure out that now for a smooth problem, it gives you the a priori convergence rate according to theory of 2. Now you are happy because now you know that up to that point, your implementation, you know that everything works for linear and everything works for quadratic. All right, now we move to cubic. So what do? The same, which is,
Try one element.
now I tried one element with a function that is cubic. My function is cubic, so I assume that I know my u of x, that is a cubic function. So I plug it here, and I get my equivalent body force. With that body force, I solve the problem, obviously respecting boundary conditions. I should get error 0. Okay, that works. Then we do, it works for one element. We do what? Well, we do 2 elements, but most likely, because the assembly was working for the quadratic case, it's also going to work for the cubic case. So most likely you're going to get the right formulation. And so say it doesn't work anymore. Oh, my formulation is wrong. Now I have to look for bugs. Be careful very much that when you are increasing the polynomial interpolation order, you have to look very careful at the number of integration points. Remember, n integration points integrate exactly a polynomial of order 2n minus 1. And so when you are looking at whatever you are integrating, it is not the same thing integrating the stiffness matrix as integrating the body force. Right? It is not the same, because in the body force you have polynomials. In the stiffness matrix you have the products of the derivatives of the polynomials. You have to be very careful about these things.
Yeah, but
Yeah?
if you just pick an order which is greater than the one that you're supposed to use,
Yeah.
you're just gonna get a solution which is not more accurate than the previous one, because you just picked a point more than what you're supposed to. So
Mhm.
even if you keep the same number of Gauss of the interpolation points
Yeah.
in the body force and the stiffness matrix, shouldn't it not matter?
I am not understanding your question very well, but what I'm trying to say is that you have to be very careful with the number of Gauss points that you need to integrate the body force and the stiffness matrix. And you have to be careful about this. Of course, you need to integrate something properly, right? It has to be well integrated. So if you look at the code, the way it is structured, you only have one loop to integrate the stiffness matrix. So if you happen to add right there your body force, then you have to be a bit careful, because normally we use the least number of Gauss integration points to integrate the stiffness matrix, because we're dealing with polynomials, and we know that polynomials we can integrate exactly. In your project, your body force, it is not a polynomial. What is it? It's a rational function. Can we integrate exactly a rational function? Nope. And so what are we going to do?
Increase the number of Gauss points.
We're going to increase the number of Gauss points until
Convergence.
we don't see any what? until we don't see any apparent difference with the result. So be careful with these things. Yeah.
But in the book there was also something stated about that in general, for if your order is of your order of your polynomial of your p-van, basically your p is the amount of Gauss points you need to get a correct assumption that still holds here, right?
Again, be careful. 1D, 2D, 3D, where it's different. It's not the same, right? So you have to think a little bit about this. And actually, it is one of the exercises of the project to help you think about how many integration points you're going to be using for the stiffness matrix for your force vector. It's one of the things that I want you to think about. Okay. But this is the way we test our formulations. It is essentially very straightforward. Once we are confident that our implementation is okay, then this is the way we test it. We don't go crazy. We don't say, okay, I'm gonna solve my original problem with my body force, and I'm gonna just check whether it works. No, we don't do it like that. Okay. If anything, if you want to take anything from this class, is when we're doing computational mechanics work, we are working with baby steps. We do building blocks and we build on top of those building blocks. And only when we are sure that everything works, we go to the next level of complexity, always. And then we can create very, very advanced and complex pieces of software, but being sure that everything that we have done so far makes sense and it's working. Okay, guys, 32 minutes. I'll stop here the video and then we can continue talking because we still have a few minutes. Yeah.